Welcome to Lesson 11C, the Theta-Beta-M Oblique shock relationship. In this lesson, we'll derive the Theta-Beta-M relationship for oblique shocks and discuss its significance. Here's the vector diagram plot that I sketched last time. This is a cleaner version from my fluid mechanics textbook. I'll fill in some of these angles. This is also beta, the oblique shock angle. This angle theta is the turning angle, where for flow over a 2D wedge, the oblique shock turns at angle beta, but the flow itself turns at angle theta, which for a wedge is the same as wedge half angle delta, since the flow is then parallel to the surface of the wedge. A little trig shows that this angle is beta minus theta, and therefore this angle must also be beta minus theta. 1 is before the shock and 2 is after the shock. Now we need to figure out how theta, beta, and M1 are related. The answer is an equation called the Theta-Beta-M relationship.
That's really a lame name, dude.
Yeah, Joe, I guess they couldn't think of a more clever name.
I'll derive that relationship here. From the diagram, the tangential component V1t is V1n over tangent beta. We can see that here. Similarly, V2t is V2n over tangent beta minus theta, as we see here. But as discussed last time, the tangential components V1t and V2t don't change across the shock. That is, V1t equal V2t. So we equate these two equations and write our result as a ratio V1n over V2n, which turns out to be tangent beta over tangent beta minus theta. I'll call this equation 6, following my equation numbers from the previous lecture. Now recall our normal shock relations. We had rho 2 over rho 1 equal V1 over V2 equal gamma plus 1 M1 squared over 2 plus gamma minus 1 M1 squared. Now we plug in the normal component, where from last time M1n equal M1 sine beta. So the normal component equation for our oblique shock is found by using V1n and V2n and M1n, since as we said previously, the normal component of Mach number or velocity is what changes across a shock exactly like the changes associated with a normal shock. So this equation becomes V1n over V2n equal gamma plus 1 M1n squared over 2 plus gamma minus 1 M1n squared. And then plugging this in, we get this equation, which is the ratio of the normal components of velocity across an oblique shock. I'll call this equation 7. Now we have two equations for this ratio V1n over V2n, equation 6 and equation 7. So let's equate them, and we get this, which I'll call equation 8. This is our desired relationship between beta, theta, and M1. But we want to get it into a more useful form. This will involve some trig identities. This one many of you will remember. Cosine of 2 beta is cosine squared beta minus sine squared beta. And you probably don't remember this one. Tangent beta minus theta is tangent beta minus tangent theta over 1 plus tangent beta tangent theta. I had to look that one up myself. Of course, we have our standard identity tangent theta is sine theta over cosine theta. And cotangent beta is 1 over tangent beta. We combine all of these and do lots of algebra, which you're welcome to do on some cold rainy night when you have nothing better to do. And what we can do is isolate theta on the left side of the equation. We get tangent theta is 2 cotangent beta times m1 squared sine squared beta minus 1 over m1 squared times the quantity gamma plus cosine 2 beta plus 2. This is the famous Theta-Beta-M equation for oblique shocks. Here we're applying it at M1 because this relationship requires us to use the upstream Mach number. But it's called Theta-Beta-M, not Theta-Beta-M1. This is our workhorse equation for oblique shock analysis. I give the caveat that this is valid only for ideal gases. I'll give some comments about the Theta-Beta-M equation here. First, theta is a unique function of m and beta. So if we pick some beta and some m, remembering that this is m1, we can get theta. Explicitly, Theta is the arctangent of the quantity on the right, which I duplicated here. In other words, this equation is explicit for solving for theta. By the way, I'll call this equation 9 as well, since it's really no different from our first equation 9. So from this equation, we should be able to plot theta as a function of beta and m1. And that's what most people do, and they call it the Theta-Beta-M plot, which is another clever name. Here's a procedure for how to create this plot. You pick an m1. I'll pick 1.1 as an example. Then you create a range of beta. In Excel, I pick my range as 90 degrees and decreasing in rows in Excel. We start at 90 degrees, which is the special case of a normal shock. We use equation 9 to calculate theta at each of these betas and at this m1. In Excel, I make another column and calculate these values of theta. Once I have these two columns, I plot theta versus beta at this m1. Then I repeat for other values of m1. This is how we generate the Theta-Beta-M plot. I'll sketch it here. Typically we plot theta versus beta from 0 to 90 degrees, and theta, the turning angle, goes from 0 to some maximum, which is approximately 45.6 degrees for air, which is the maximum possible turning angle for an oblique shock in air. This occurs at a Mach number m1 of infinity. For Mach numbers less than infinity, the curve does not rise as high. But all of these curves go to 90 degrees on the right, which represents the normal shock. This is not to scale, but these small curves down here will be Mach numbers close to 1, and the curves get larger as m1 increases. So each Mach number also has a unique minimum beta. The minimum beta represents the weakest possible oblique shock at a given Mach number m1. It's where theta equals 0, as we see here. Well, this is a Mach wave, where beta equal mu, the Mach wave angle, which is arcsine of 1 over m1. For example, at Mach number 1 equal 1.50, mu equal 41.8 degrees. So that would be this location here. Keep in mind that this plot is for air. It would look similar, but with different values and slightly different shapes for other gases. I'll make a comment here. We call this beta beta min, and it is impossible for beta to be smaller than beta min for a given m1 and gamma. This is the figure from my undergraduate textbook. Recall that we use ma instead of m for Mach number, but the figure is still useful. Here's the peak theta of 45.6 degrees, and here's my 41.8 degrees for beta at Mach number 1.5. Some authors like to turn this plot 90 degrees, plotting theta horizontally and beta vertically. It's the same information, just with the axes flipped. I prefer plotting it this way, which is the way I did it in the book.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3.